Hey guys, today I'm going to teach you guys a little bit about stoichiometry and the mole ratio. So let's go ahead and jump into this. All right, so here we go, the mole ratio. So in order to do stoichiometry, we need to understand a little bit about the mole ratio. And when we're doing stoichiometry, we have to have a balanced chemical equation. And that's why we spent so much time making sure you're comfortable with balancing chemical equations. First off, let's talk about stoichiometry. Stoichiometry specifically refers to the relationship between reactants and products in a chemical reaction. Let me show you what I mean by this. Imagine you invited a couple friends over and you wanted to make sandwiches for your friends. We're just going to do simple grilled cheeses here. And so you have three friends over and you want to make a sandwich for yourself too. So you need to make four sandwiches. So if you want to make four sandwiches, how much stuff do you need? How many reactants do you need? Well, you would need to have 8 slices of bread, and you would have to have 4 slices of cheese. This kind of intuitive math here is a great metaphor, a great example for doing stoichiometry. If I knew I needed to make 4 sandwiches, how much stuff should I start with? And chemistry is going to be exactly the same way, right? If I want to make a certain amount of a chemical product, how much reactants should I buy? Should I start with? So yeah, a balanced chemical equation shows the amounts of reactants and the amounts of products um in that chemical reaction, right? So when I'm looking at this balanced chemical equation here, I have 2H2O decomposing into 2H2 and 1O2. And quite literally, when I see 2H2O, I'm referring to two molecules of H2O. They're breaking apart. The hydrogen atoms are finding each other and forming chemical bonds, and the oxygen molecule is finding the other oxygen atom as well. Okay, so these chemical equations, the balancing is super important, and they're showing the amounts of reactants that are reacting and the amounts of products that are being produced. Okay, so let's go ahead and consider this following chemical reaction: the combustion of methane. Hopefully, we know based on this balanced chemical equation that one molecule of CH4 reacts with two molecules of O2 to make two molecules of water and one molecule of CO2. So those coefficients are kind of telling us certain things here. And once again, the coefficients correspond to the relative number of particles on the reactant and product side. So this is just a little bit of review. Hopefully there's nothing new here. So the coefficients show the ratios between the molecules of reactants that are reacting and the ones that are being produced. For example, one molecule of CH4 will react with two molecules of O2. If this is a ratio, that means that once again, one molecule of CH4 is equal to one molecule of O2. Nope, sorry. Two molecules of O2. And where did that one and two come from? That one and two came from the balanced chemical equation. And I can relate any two chemicals to each other, right? I can say two molecules of H2O are equal to one molecule of CH4. Where did those numbers come from? They just once again come from the balanced chemical equation. All right, so now that we kind of have that down, how do we actually go about using these? How do we go about using these ratios here? Okay, so how many molecules of O2 will react when 25 molecules of CH4 also react? All right, so if I'm going about this, you probably already have it in your brain that you're like, all right, well, if it's 1 to 2, 2 times 25 is 50, right? And that's exactly right. But we want to make sure we set up our dimensional analysis. So if I have 25 molecules of CH4 and I establish the ratio of 1 to 2 before, then what unit do I want to get rid of? I want to get rid of the molecules of CH4. and I want to go towards molecules of O2. I know that's a 2-to-1 ratio. Where did I get those numbers from? I got them from the balanced chemical equation, 2-to-1, and 25 times 2 is equal to 50. The molecules of CH4 cancel, so that's 50 molecules of O2. All right. Let's go ahead and try this with a little bit trickier one here. The math doesn't really change, but the numbers are going to be a lot more representative of these things, right? So, oops, sorry about that. How many molecules of CO2 are produced if 5.98 times 10 to the 18 molecules of O2 reacted? All right, so I have 5.98 times 10 to the 18th molecules of O2. I know that for every 2 mole molecule of O2, 1 molecule of CH4 reacted. That means 5.98 times 10 to the 18th divided by 2 will get us the answer. And I believe that's, yep, that's right. 2.99 times 10 to the 18th. Oh, that was ugly. Let's do that again. 18th molecule of CH4 reacted. All right, let's go ahead and try, let's go ahead and see how this actually relates to moles, right? So we know, right, that one molecule is, excuse me, 1 mole is equal to 6.02 times 10 to the 23rd particles. So since the ratios are always going to be 1 to 2 to 3, right, depending on what the coefficients are, since 1 mole is equal to this number, we can also use the molecule ratio as if it were a mole ratio. The mole ratio is a conversion factor that relates the amounts of reactants and products to each other. The mole ratio comes from the balanced chemical equation. So let's go ahead and check out this reaction here. Once again, the key pieces for this reaction are the coefficients, right? So 1N2 plus 3H2 yields 2NH3. So when I'm looking at this, I know that 1 mole of N2 reacts with 3 mole of H2 to produce 2 mole of NH3. Now, when I'm using this, I'm going to use it in the exact same way. How do I create these mole ratios? Well, the way I do this is by quite literally just looking at the balanced chemical equation. So to create the mole ratio, we look at the equation. And so let's say I want to do the mole ratio between N2 and NH3. Well, I know that 1 mole of N2 is equal to 2 mole NH3. And this, once again, just comes from the numbers that are here. And it doesn't matter what chemicals I'm relating. If I was looking at N2 and H2, I would say 1 mole of N2 to 3 moles of H2. But I was just asking about N2 and NH3 for this particular example. All right, so let's go ahead and check this out here. How many mole of NH3 are produced when 94.8 mole of N2 react? So what I want to do is I want to look at what chemicals I'm dealing with. I'm dealing with NH3 and N2, and I know once again that for every 1 mole of N2, this is equal to 2 mole NH3. For this particular problem, I didn't ask about hydrogen. Hydrogen absolutely is present and part of the chemical reaction, but we're just dealing with NH3 and N2. So I know that 94.8 mole of N2 reacted. I'm going to set up my dimensional analysis. I put the unit I want to go away down below, mole of N2, and I'm going towards mole of NH3 above. And I know for every 1 mole of N2, 2 mole of NH3 are produced. That means 94.8 times 2 gets me 189.6 mole of NH3 was produced. So whenever you're doing these particular problems here, you want to identify the 2 chemicals that are reacting or are being produced, find the coefficients in front of them, and set those two things equal to each other. And then you guys know how to do dimensional analysis. Awesome. All right, guys. Thank you so very much. I hope you're having a great week, and I'll see you when I get back. Bye.